All right, good morning, everybody. So today we are finishing up chapter 4.1 and maybe going through some of 4.2 in Vakil. Um, the big thing is that we did not finish off this definition about structure sheaf modules coming from A modules. Um, And so yeah, basically we said that if M is an A module, then we can describe a sheaf on the distinguished base. Um, and so basically, this MDF is the localization of the multiplicative set of functions not vanishing outside of VF. Um, Restriction maps work reasonably. Um, And then we claim that this is a sheaf on the distinguished opens. Then it's a sheaf on spec A. And then it's a structure sheaf module. Um, and so, yeah, I guess we really want to figure out a few things. So I think we're given that it's a pre-sheaf, right? I think we're given it's a pre-sheaf. Pre-sheafness. um, then we want to show base identity and glueability on the distinguished opens, and then spec A. And I think it's worth noting that if we show it just for spec A, we do end up getting the other one. Sorry, I'm tired. I'm on vacation, technically. You
Yeah.
wouldn't know it. Um, so, um, first thing for identity, we want to show for every U, I guess really for every FI, D of FI, um, if um, is a cover of DFI. Um, and F1 and F2 are in M tilde over DFI as a section. And F1 restricted to, let me call these DGJ. DGJ is equal to F2 restricted to GJ, then F1 is equal to F2. Okay. And then the second thing we want to show is the glueability axiom, which says that if set of D GJs covers DFI, and we're given FL in the section over for all L such that FL intercept evaluated at GFI intersect nope DGI DGJ is equal to FK evaluated on the same intersection for all L and K. Then there exists some F in DFI such that the restriction map from DFI to DGI is equal to F is equal to Fi. Okay. So the tough thing here is really just kind of like keeping track of what we have shown, what index notation is out there. So for proving one, we're given everything up till here. Yeah. Um, So let F1 and F2 be in the structured module over DFI. With then what induced property are we pulling from here? Like what induces?
Is this something on spec yet?
Wait, hold on. I think it's that this is for all J, right? Hold on, let me check the definition. I feel like this is the thing that we always forget. Yeah, it's for all J. So basically, for every distinguished, open cover, right? Every distinguished open cover agrees. And so then the only place that they would disagree would be on closed sets. No, that's not necessarily the case. Hold on, let me check something real fast. Oh, so that's not how I saw that working. Okay. So Math Stack Exchange has once again duped us. Um, this is not an easy proof.
Uh,
Um, so consider the sequence. Um, okay. Um, and what is this called? Hmm. So if alpha, I'm gonna claim if alpha is injective, this is the same notion as identity. And then if cur beta is contained in M alpha, this is the same notion as fluidity. Um, and I guess the thing I'll note is that alpha sends S to S restricted to DFI. But then beta sends SI to SI D FI FJ minus SJ and D FI FJ. Right, because this measures the distance um, between things, which on the intersection should be 0. Um, okay, so things things that we should know. So, okay. Injectivity of alpha means that for any two SIs which are equal, the S in alpha inverse needs to be the same. And that is definitely uniqueness, right? So this makes sense. And then for gluability, anything that goes to 0 here is anything which agrees perfectly on intersections. And if that kernel is contained strictly within the SIs, then those are all of the gluable functions on intersections. Does this make sense?
Yes.
Okay. And so now we maybe want to look for a trick. Okay. So now consider that D of Fi is really is that true? No, it corresponds to, right? It's really the variety of the ideal, right? And since is compact, we can reduce our DGIs to a finite subcover 1 through n. So DFI is equal to the union of DGIs I equals 1 to n, which then corresponds to the variety of the radical ideal of G1 through Gn. This means that there exists an N in Z and AI in A, which is our ring. Really, we're talking about spec A, but we just have a base for the topology on spec A.
Yeah.
Such that f to the n is equal to the sum over I of AI Fi. Okay. So now we want to show that alpha from M to the product on M localized at Fi and I is injective. And I'm just going to note that this is isomorphic to A localized at Fi, and I'm realizing that this is the product of GIs. GI, GJ. So you need me to walk back through anything now that I've needed to change this notation?
Nope.
Okay.
And no, if I see an FI, we just change it to GI pretty much. Well, not all of them, but
Yeah. Yeah. All right. There we go. So now we want to show that this is injective. Um, right. So let S in AFI restrict to 0 in each MGI. Then S has to be the form A over G to the M. No, this is F to the M. Then in no, not F N I. G to the Ni. A equals 0 in MGI. Um, and then if we let N be the max of these Ni's, then GI to the N times A is equal to 0 for all I, since F ooh. I am realizing that this was in fact Fi. Since Fi to the N is the sum of the AI GIs. Um, let M prime be such that Fi to the M prime is in the ideal of F1. Nope, not F1. G1. G. Oh no. We're gonna reindex this at K. Okay, now it works. Okay. Um, um, then just by definition, F to the M prime times A is equal to A times the sum I equals BI FIN, which is exactly equal to A times 0, which is 0 in MGI. But in AFI, which is equal to M, F is invertible. So FIN A equals 0 implies that A equals 0 since M is integral. Hence, S equals 0 in AFI, and alpha is injective since its kernel is trivial. Does that make sense?
Yeah.
Okay. So then I really hope gluing is short. It's not. Oh, okay. All right. Let's try and do this quickly. So let SI in nope, A of GI. Sorry, S equals 0 in A of GI. Be sections such that for all I and J, SI restricted to M, GI, GJ is equal to SJ, M, GI, GJ. In M. I guess this is what we would call. No, we're gonna. So, okay, just to make this clear, because I keep switching the notation on accident, this is also equal to AGI, right? Since I'm following a math stack exchange proof outline. So if I ever switch that up, so let SI be equal to AI divided by fi to the m. And then that for all I and j, there exists Tij such that in AFI, which is equal to m, fi fj to the t ij times fj to the m ai minus fi to the m aj equals 0 for all nj. And so this is by the really big picture that we drew last time here. So this is that. Except we've already used m, so we're going to call this t. Moreover, we're going to back up the fact that we can get this t to be universal. And so then let f I to the n be the sum of ai and gi. And I'm realizing that, once again, all of these were g's. And that should be a g. There we go. In uh, a candidate numerator for f restricted to ui equals fi. A equals the sum ai git let's not use ai, let's use in so this is specific to mgi, which is contained in mgi to the t. And then this is in m. And so then wait, this is no longer a. Why did I write A? If this is S, then S restricted to GK is equal to the sum over I of CI GI to the T SI in GK. On GI GJ, SI equals SK by compatibility on intersections. So S is equal to the sum over I of CI FI F K to the T minus 1. Okay, that's not making sense. Well, because it's G, but the T minus 1 is still not making sense. SK. Which is equal to, nope, that's GI. This is equal to Fi to the capital N G KT minus 1 SK. I'm confused on this.
Yeah.
Where the heck did that come out of? Oh, because we're pulling a GI out. See? Like there's a GK times GK to the T minus 1 equals GK to the T. Does that make sense?
Yes.
Okay, that makes sense. Anyways, so then since Fi is invertible on DF and FK, no GK is invertible on does not vanish DFI. No. DGK. We can divide by Fi to the N GK to the T minus 1 inside M GK and obtain that S restricted to M GK is equal to SK. So the SIs in GK glue to S in M. Okay. It's not explicitly clear that this is showing that the kernel is contained within the image, because that's not actually how they ended up proving it.
Yeah.
But it is clear that this is gluing, right?
Right.
And so not how we did it. It's worth noting that there's a standard generalization from the distinguished base of opens to any other topology base for spec A that this just kind of works. Um,
You mind going up just a bit?
yeah, here.
Thank you.
All right.
All right.
Cool. Okay. Hmm. Okay. So now our last thing for today will be describing O spec A modules. Um, so recall that an OX module is a sheaf of abelian groups on X such that for every open in X, its section is a module over the structure sheaf, restricted to that open. Right. And so basically what we've constructed is X is spec A. And so we've partitioned spec A into opens with distinguished opens. So for every U equal to DFI, then we have, spec A over U as a section is a module with coefficients from the structure sheaf. Um, and so really when what we say, and this is um, where we say like equivalently M over U as a section. Um, and let's just call this DF. Because that's just gonna make life easier. M over DF is the localization at F. Because that's where we can get coefficients.
Okay.
And then we have restriction maps where if DF contains DG, then there's a natural inclusion map. Wow. MF to MG. So basically O spec A, DF is the localization of our ring at F. And then MF is an AF module. And restriction maps are AF linear. And so basically, into the product of MGI, which is equal to the product of AFI, or AGI, sorry. Is basically the sections functor on M. So another way of picturing this is like with the global sections functor, this is what we called gamma, where if you had like gamma and a pre-sheaf, you know, send stuff, um, from X to OX on UI for I, right?
Yeah.
So we have kind of like bundles of AF modules, which bundle together to be a larger module.
Right.
Um, so yeah, we're gonna talk about this more in chapter 6 with quasi-coherent schemes. But yeah. Also this sequence being exact, if our GIs generate A, um, basically we're talking about an exact sequence of modules, and like alpha and beta are very important later on in life, if that makes sense.
Okay.
So we did not actually finish 4.1 today.
Hmm. Would you mind going down to that last
Oh
part?
wait, no, actually we totally did. Hold on. Okay, what do you need?
Just the very last part with the sections functors. Thank you.
Okay, we did the exercise. There is okay. There's an exercise that we didn't do.
Okay.
We did exercise 4.1.f as part of our proof technique.
Yeah.
Um, we need to do 4.1. So, okay, so next time tomorrow, we need to do 4.1.e, and we need to do 4.1.g, and then the definition 4.1.7. And then 4.2. And those should be pretty fast.
Mm.
And 4.2 is nicer because it's about visualizing schemes.
Oh, perfect.
And 4.3 is mostly definitions, and so is 4.4. And since we're doing a double session tomorrow, we can probably get through a non-trivial amount of chapter 4.
Awesome.
So, all right, I will go ahead and turn off the recording. Yeah.